Hi everyone, this is Dr. J. Ravindranath Reddy. So we are discussing the course of numerical methods and integral transforms. In that we are discussing numerical integrations. So in this video we are discussing about the numerical integrations. So before discussing the numerical integrations, we will see why we have to apply these numerical integrations. So suppose I have given a function. So I have given one integral 0 to 1 and x square dx. So now whenever the function is known, then by using our standard integral formulas we can find out the integral of 0 to 1 x square dx. Suppose I have given another integral 0 to 1 f of x dx. So here, in order to apply the standard integral formulas, we don't know the function. So here he has given a unknown function f of x. So whenever we are having unknown function, for that unknown function, whenever we want to find out that integral value, then we can go to the concept of numerical integration. And suppose whenever the function is more complicated to find out the given integral, then in that case also we can go to the numerical integrations here. So these are the cases where we can use this numerical integration. So numerical integration is a method to calculate the approximate value of an integral using the numerical techniques. So numerical integration is nothing but a method which is used to find out the calculate or to find out the approximate value of the integral by using the numerical techniques. Now there are various useful interesting methods for the numerical integrations. So there are so many methods we are having under this numerical integration. That methods are trapezoidal rule, Simpson's rule, Gauss, Newton's, Leibniz rules. So these are some examples we are having. So in the similarly, whenever sometimes the integration becomes too hard to evaluate the integral value here. So that means whenever we are having a complicated function to find out the integral, that in that case also we can use numerical methods to find out that integral value here. So these are the different uses or different cases or different methods we are having under the concept of numerical integration. So now in our syllabus we are having a trapezoidal rule, Simpson's 1/3 rule and Simpson's 3/8 rule. So trapezoidal rule, Simpson's 1/3 and Simpson's 3/8 rule. Now by using these three methods, we will see how to evaluate the given integral using these numerical integral techniques. Now first we will take the standard formulas of trapezoidal, Simpson's 1/3 rule and Simpson's 3/8 rule one by one, and then we will go for the problems how to use these formulas to find out that integral values. Now first we will take the trapezoidal rule here. So we will consider this is the standard integral x0 to xn some function y into dx is equal to h by 2. So h is the h is the step length between the values of x, and y0, yn, y1, y2, y3, and these are the values of y. So all these values we have to find out, and if you substitute that values in this standard formula, then if you simplify this, then we can get our required integral value here. So here we are having some conditions. In the trapezoidal rule, we can divide the interval x0 comma xn, we can divide this interval x0 comma xn into any number of subintervals here. We don't have the particular condition in the trapezoidal rule. The number of subintervals must be only this number of subintervals, or only even subintervals, or only odd subintervals, or we don't have any conditions like that. So we can divide into any number of subintervals. This is the important point we have to remember. Now when you go to the Simpson's 1/3 rule, so we will use this formula to find out the Simpson's 1/3 to find out the integral value using Simpson's 1/3 rule. That is h by 3 into y0. This is the initial value of y and this is yn is the final value of y in the table. So y0 plus yn plus 4 into y1 plus y3 plus this, we have to take the odd ordinates of y values, plus 2 into, here we have to take y2, y4, y6, y8 and y10 and so on. This is even ordinates we have to consider here, and you substitute all the values of y which we got in the table, and if you simplify this, then we can get our required value for the given definite integral. And here one important condition we have to remember whenever we want to apply this Simpson's 1/3 rule. So in the Simpson's 1/3 rule, we have to divide the number of subintervals. We have to divide this interval is x0 comma xn into only even number of subintervals only we have to consider. So if you imagine that the number of subintervals is represented with n represents the number of subintervals. So this number of subintervals n value should be 2, 4, 6, 8, 10 and so on. We have to consider only these even values only. So whatever we take the large value of n we consider, then we will get more accurate value than compared to the previous one. Suppose one student has taken n is equal to 4 and another student has taken n is equal to 6, that is number of subinterval 6, and another student has taken, the third student has taken the more number of subintervals when compared to the remaining students. So whatever the answer we got for the third student, so this answer will be more accurate than compared to the remaining two students. Why? Because as the number of subintervals, if you take more number of subintervals, then we will get more accurate value than compared to the remaining. Okay, this is the condition we have to remember. If you take more number of subintervals, you are going to get more accurate value for the given definite integral. So in the Simpson's 1/3 rule, the number of subintervals must be even. That is the condition we have to remember. Now if you go to the next one, Simpson's 3/8 rule. So this is the standard formula we will use. This is this integral x0 to xn y into dx is equal to 3h/8 y0 plus yn. This is common for all the three formulas, y0 plus yn, and plus 3 into y1 plus y2 plus y4 plus y5 and so on. This plus 2 into, here we have to take the ordinates which are multiple of 3. Multiple of 3 is nothing but y3, y6, y9, y12, y15, like that we have to consider this. Okay, so this is our standard formula we will use to find out the definite integral value by using Simpson's 3/8 rule. And in this Simpson's 3/8 rule also, we are having some condition with respect to the number of subintervals. Now we will see what is that condition here. So in the Simpson's 3/8 rule, we can divide the interval x0 comma xn. This is our interval. We have to divide this interval only in the multiples of subintervals, multiples of 3 subintervals. So multiples of 3 is 3, 6, 9, 12, 15 and so on, whatever the values we get in the third table. So this number of subintervals we have to consider whenever we want to apply Simpson's 3/8 rule. So we can take n is equal to 3, or we can take n is equal to 6, we can take n is equal to 9 and so on. These n values must be a multiple of 3 in the Simpson's 3/8 rule. So these are the conditions we have to remember, and these are the formulas we have to remember to complete our numerical integration, numerical solutions for the given definite integrals. Now we will take one by one, we will take the problems, and one by one we will take the method, and we will see how to apply that methods to find out that integral values here. Now find the value of integral 0 to 1 by 1 plus y square dx. This is the function he has given, and we have to find out this integral value between the limit 0 to 1 with respect to x. And now we have to find out this integral value by using trapezoidal rule. He has mentioned the method. So by using this method, we have to find out this integral value. Along this method, he also given some number of subintervals. So we said that we will represent that number of subintervals with n. So n value he has given us 5. Based on this n, we are going to divide this interval 0, 1 into subintervals, into 5 subintervals here. So here, since n is equal to 5, we don't have any condition for the trapezoidal rule. So even number of subintervals or odd number of subintervals like this, we don't have any condition in the trapezoidal rule. So we can take any value for n in the trapezoidal rule. That is the point we have to remember. Now, so this is our function, or we can take y is equal to f of x is equal to 1 by x square. So our standard definite integral what we have taken in the formulas is, it is represented as x naught to xn y into dx. So y, we can consider y is equal to f of x. So we can consider this function here 1 by 1 plus x square, and here he has given x naught. You take the lower limit of this integration. So this is our lower limit here. So this is our lower limit 0, and this is our upper limit 1. So x naught is equal to 0 and xn is equal to 1. So the lower limit is represented with x naught and the upper limit is represented with xn. Now the number of subintervals he has given in the problem itself, he has given the number of subintervals. So he has given that n is equal to 5. Now based on this, we have to find out h value here. So h is equal to xn, that means upper limit minus lower limit by number of subintervals. So we want n is equal to 5. So based on this number of subintervals, we have to find out the difference between the values of x, that is represented with this h we can call it as a step length, or we can call it as a step size, or we can call it as a difference between the values of x. We should have a common difference here. So 1 minus 0 by 5, which is equal to 1 by 5, which is equal to 0.2. So we got h is equal to 0.2. Now we got h value, we got n value, and we got the interval 0, 1. Now based on this, by using this, we are going to construct the table. So first you take x naught value, x naught initial value of x, that is 0. And now if you want to find out that x1 value, next value of x, that is x1 is equal to x naught plus h. X naught is equal to, we got 0, and h value is equal to 0.2. So you will get 0.2. So you consider this 0.2 as x1. Now similarly, if you want to find out this x2 value, take the help of previous value, that is x1, and for this x1 you add h value here. So x1 is equal to 0.2. For this 0.2, add one more 0.2, you will get 0.4. That 0.4 is represented with x2. And similarly x3. x3 is equal to its previous value. Our previous value is x2. For this x2, add h value. That is 0.4 plus 0.2, 0.6. Like this, you continue this taking the values of x until we get our upper limit. So this is x3 plus h 0.8, and x5 is equal to previous value, that is x4 plus 1, plus h. So 0.82 plus h 0.2, 0.8 plus 0.2, you will get 1. So no need to go for the next one, because we are having the upper limit as 1. So from 0 to 1, we have to divide into subintervals. So this is one subinterval, and this is one subinterval, and this is one subinterval. So totally we are having 5 subintervals. This is first subinterval, second subinterval, third subinterval, fourth subinterval, and this is fifth subinterval. Okay. So like this, we have to divide that interval 0, 1 into 5 subintervals. And now for these values of x, we have to find out its corresponding y values. So at the beginning we have taken y is equal to 1 by 1 plus x square. You take this condition, y is equal to 1 by 1 plus x square. Now you take the first value of x and get the y, first value of y, that is y naught. So y naught is equal to, so 1 by 1 plus, we are taking this y naught value, we are finding this y naught value by taking its corresponding x value. What is our corresponding x value for this? X naught. So x naught square. So 1 by 1 plus x naught. X naught is equal to 0, 0 squared 0. So 1 by 1, you will get this value is equal to 1. So like this, similarly, you take y1. y1 is equal to 1 by x2 plus x1 square, because y1 is the value of y at x is equal to x1. So at x is equal to x1, we are getting this y1 value. So x1, we have to take the help of x1 to find out the value of y1. So this is equal to 1 by 1 plus x1 is 0.2 whole square. Now simplify this, you will get our y1 value. So like this, we have to take y2, you will get y3 and y4, and finally you will get y5 values. So like this, we have to construct the table by using the given data. Now we are having y0, y1, y2, y3, y4 and y5. Now by using this table, we are going to take the trapezoidal rule formula. In that formula, we are going to substitute that y0, y1, y2, y3, y4. Then if you simplify this, we can get our required value here. So now this is our formula. So in the table, the first value of y is y0 and the last value of y is y5. So we are taking that. So h by 2, formula h by 2, y0 plus y5 plus 2 into y1 plus y2 plus y3. We have to take the remaining values here. Now you substitute that y0 value, y5 value, y1, y2, y3, all this, you substitute all these values from the table and simplify this. And h value, we got that h is equal to 0.2. So you take h is equal to 0.2 by 2 and simplify this. We will get our required integral value here, 0.783734. This is our integral value, approximate value here. So whatever the value we get by using our standard formulas, integral formulas, we can call it as a exact solution. And whatever the solution we get by using numerical methods, we will get approximate solution. So this is our approximate solution here. So this is the way how we can apply this trapezoidal rule and how to get that integral values by using trapezoidal rule here. Now we will take another problem by using Simpson's 1 by 3rd rule. So we have to evaluate this integral value, integral 1 to 2 1 by x dx using Simpson's 1 by 3rd rule, and we have to get this log 2 base e value here. Now as usual, so you get the values of x0, xn, and the interval is, our interval is upper limit, lower limit 1, 2. So I want to divide. He has in this once, if you observe this one, in this problem he has not given the number of subintervals, whereas in the previous problem he has given the number of subintervals. So according to that number of subintervals which are given in the problem, in the previous problem, we have taken n value, and whenever number of subintervals is not given in the problem, then according to the condition of Simpson's 1 by 3rd rule, we can take any value for n number of subintervals. You can take, the condition is our n value, the number of subintervals must be even. You should not forget this point. So even you can take n is equal to 6 or n is equal to 8 or n is equal to number of subintervals equal to 10 also. So but I am taking 8 number of subintervals here. So if you consider 8 number of subintervals, we will get h is equal to 0.125. So in the previous we have seen how to get the value of h. So h is equal to xn minus x0 by n. xn is upper limit, that is 2 minus 1 by 8, which is equal to 1 by 8. This is this value here. So similarly, construct the table. So this is by default the initial value of x is x0, and this is x1, and this is x2 value. So like this we have to get up to the final value is x8, and its corresponding y values y0, y1, y2, y3, y4, y5, and so on up to y8. Okay, so we have seen how to construct this table in the previous problem. Follow the same procedure and get the values of y0, y1, y2, y3, and so on y8. So once if you construct this table correctly, then automatically we can get our required solution here by taking that standard formula. Now Simpson's 1/3 rule. So first ordinate is y0, so you take y0, and the last ordinate, last value of y is y8. So you find the sum of first and last ordinate plus 4 into y, you take the odd ordinates, that is y1, y3, y5, y7, plus 2 into even values y2, y4, y6. So don't consider this y8 once again. Already we have completed this y8 at the beginning itself. So we should not repeat the values of y. We have to use the values of y only once in a formula. Okay, now substitute all these values here. We can get our required solution 0.6931. This is our numerical solution by using Simpson's 1/3 rule. Now we will find out that integral values here, actual integration. So integral 1 to 2, integral of 1 by x, we can take it as log x. So substitute the limits, log 2 minus log 1, log 1 is 0. So you will get log 2. This log 2 value is equal to whatever the value we got here. So this is the way how we can apply this Simpson's 1/3 rule, and how we can compare the numerical solution with the exact solution what we got by using these standard integral formulas. So now we will take one more application. This is a real-time application we can consider. So a rocket is launched from the ground. Its acceleration is registered during the first 80 seconds and given in the table. So use Simpson's 1/3 rule. Find the velocity of the rocket at 80 t is equal to 80 seconds. So this is the table he has given. At initial stage, the acceleration is given. After 10 seconds, this is the acceleration. After 20 seconds, this is the acceleration. So for every 10 seconds, he has measured the acceleration. So this is the data given. Now from this, by using this data, we have to find out the velocity. We have to find out the velocity of the rocket when t is equal to 80 seconds. So now if you want to find out the velocity, first we have to derive the relationship between velocity and acceleration. So we know that the rate of velocity is acceleration. Definition of this acceleration, that is F is equal to dv by dt. So apply this velocity of the rocket at t is equal to 80 seconds is given by, now we want this v here. So in order to remove these derivatives, we have to apply the integration on both sides. So we get, this is dv by dt. So the rate of velocity is called acceleration. So in order to remove this derivative here, we have to apply integration on both sides. So this derivative and integration with respect to t is gets cancelled. You will get integral v equal to integral 0 to 80 f into dt. Now we have to evaluate this integral value by using this Simpson's 1/3 rule. So once if you observe this one, f is a function, we don't know what is that function. So just we know the values of f here. So for known function, we are going to find out Simpson's integral value for by using Simpson's 1/3 rule. So now use the Simpson's 1/3 rule. Use the same formulas here. You substitute that formulas values which are given in the table. and simplify this, we will get 30.86 meters per second. That is the velocity of that rocket. Okay, the next problem is Simpson's 3/8 rule here. So this is the problem he has given. So whenever we want to apply Simpson's 3/8 rule, the number of subintervals, whenever we want to apply Simpson's 8th rule, the number of subintervals must be multiple of 3. So we can take 6. 6 is a multiple of 3, or if you want you can take n is equal to 9 also, we don't have any problem. So by default we will consider n is equal to 6, and the function f of x is given by 1 by 1 plus x square. Now this is the table we got. So we can consider x suffix I, or we can take x suffix I here, or x. So this is x0, and this is x1, x2, x3. So we know how to get these values here. H is equal to xn minus x0 by n. So you will get this value is equal to 1 by 6. H is equal to 1 by 6. Now add 1 by 6 for 0, you will get 1 by 6 here. If you add 1 by 6 for 1 by 6, you will get 2 by 6, 3 by 6, 4 by 6, and so on, 6 by 6. That is equal to the upper limit. And by using this function, you get the values of y, that is y0, y1, y2, y3, y4, y5, y6. Now use Simpson's 1/3 rule formula. So substitute these values, you will get our required integral value. Integral 0 to 1, 1 by 1 plus x squared dx by using Simpson's 1/3 rule is given by 0.7853895. This is our final value here. So like this, we can apply this Simpson's 1/3 rule, and we can construct the table by using the number of subintervals. So you consider more number of subintervals so that we can get more accurate than compared to this remaining subintervals. So in this video we have seen how to apply these numerical integrations for our problems to find out that integral values. In the next video we will go for the numerical solution of ordinary differential equations. So that ordinary differential equations we are going to discuss, concentrating only on the first order differential equations. Now for the first order differential equations, we will see how to apply the numerical methods to find out the numerical solution. For which type of differential equations we can apply, that all these things, what are the methods we are having, numerical methods we are having to solve these first order differential equations, and all these things we will discuss in the next video. Thank you.